Welcome back once more. I'm still Mr. Steele. I'm still here to work through the Essential Skills Quiz model with you for the first half of Honors Pre-Calculus at Franklin. In this time, I'm going to be talking about sketching polynomials, something that Franklin students typically kind of think of as noodle bowls, although that sounds a little bit more like an order that I might place at a restaurant. So in any event, I'm going to talk in this video about the couple different ideas that help shape the shapes of polynomial graphs. And I'll talk a little bit about some of the techniques that you can use to make sure you get your shapes looking accurate and representative of what you're trying to get. In addition, of course, I'll do the two problems that are posted on the ESQ model for you. And I'm basically doing this before dinner, hoping to then get one more in before that. So basically, I'm going to dive right in. So the key ideas here are effectively graphing polynomials. So I was tempted to skip this section, but I felt like it might be helpful just to break down the pieces that sort of form the foundation of this really quickly. Something I should note here that isn't mentioned on this page is that each of the polynomials on the Essential Skills Quiz model that you're using here and working with is always going to be provided in factored form, which certainly helps a little bit. You don't have to stress about factoring your polynomial in this case. It's always going to be provided that way, so you'll very quickly be able to identify your zeros, also known as your x-intercepts, and then by plugging in 0, you'll be able to find your y-intercept. And that can help provide a little bit of context as well. Having said that, what makes these graphs sort of interesting and memorable and a little bit challenging, I think, depending on the situation, is that there are a bunch of other little influences that will influence how the shape actually turns out in our graph. And while these things don't have to be perfect, like we're not finding maxima or minima, like high and low points at all, you still do need to make sure you go through the right points and that everything's oriented in an appropriate way and sort of shaped in the appropriate way. That's what we're going for here, something shaped, especially horizontally. That's really where we've got to make sure everything is scaled nicely. So there are three key ideas that I think are helpful to kind of put in your head before we start. And I'm not going to go into extreme depth on these. I just want to kind of put them in your head so that way you kind of get that one-stop shop in like 3 to 4 minutes. You're like, oh yeah, okay, that's all that stuff. I remember that stuff. And then you can probably attempt it on your own before potentially using the solutions themselves. Although obviously feel free to continue playing this video forever in case this ever gets monetized. In any event, I'm starting with degree parity, and I wanted to define it that way just because I don't think a lot of students are aware of that phrase parity. Parody typically you might think of parody as like a movie that spoofs something, something similar to satire, but like very closely aligned with something. Different kind of parody. This is actually the same word as like parody in professional sports, where like any team can win at any time, like the teams are more or less equal. But this is actually a different kind. Parity in the mathematical sense means even or odd. So basically the first idea I wanted to remind you of is that the degree of the polynomial, which is the highest power of any term, of course we're in factored form, so whatever, it's the degree of the leading term or the power of the leading term, is going to influence the general shape of your graph. And this is where that sort of Franklin idea of like the noodle versus the bowl comes from. It comes from whether or not your degree is even or odd. So if you have a noodle, we're talking about odd degree. And that actually is kind of interesting because noodle and odd look like they're similar. So a noodle starts in one place and ends in the opposite. So a positive noodle will look like that, and a negative noodle would look like that. I'm only going to leave the positive one. We'll talk about positive versus negative in a second. But there's the noodle where we have an even degree, or an odd degree. And then of course we have bowls which have even degree, and those resemble a parabola. Basically, it starts in the same place that it ends. It has the same left and right end behavior. That would be a positive one. Obviously, there can be more squiggles in the middle. And then a negative one. So basically, degree parity, the parity of the degree, allows us to know where the end behavior is going to land. Is it going to be opposites? Is it going to be high or same? And that will sort of distinguish our shape. Everything else is just connecting the dots through our intercepts. Now, combining with that, I've already alluded to it, is what's called the leading coefficient test. And that has to do with whether or not we're going to be going up, down, up, or down, down. And that's determined based on a combination of course, the degree, even versus odd, and whether or not your leading coefficient is positive or negative. So in other words, in this case, if I call capital D degree, and then I call A our leading coefficient, if your degree is even and your leading coefficient is positive, you're going to get something that resembles a parabola. So it will start and finish in the positives. That gives us a positive infinity, left end behavior, and right end behavior. On the flip side, if your degree is even, but your leading coefficient is negative. And it bothers me to write it that way. I'm going to do a less than 0 and a greater than 0 for the other one. It just feels weird to not do it that way. So if you have a negative leading coefficient, it's going to be the ending and beginning in the same place, but in this case, it's going to be going down to negative infinity on both the left and right end behaviors. Now take that in contrast to an odd degree. So if you have an odd degree and a positive leading coefficient, then basically we're going to have what we'd think of as like a positive noodle. So basically it's going to start low and end high, just like a positive slope line or a positive cubic. I think most people think of the cubic. On the flip side, if you have an odd degree, and I'm just going to have to write the word ODD there. It looks weird to just write 0. And then your leading coefficient is negative, then you're going to start high and end low. So basically that will influence your shape. In a sense, the leading coefficient test, that combination of leading coefficient and degree, sort of tells you everything about your graph. The rest is just basically like figuring out what happens in the middle, like how is it bouncing around or sliding around depending on the case. And speaking of bounces and slides, there's an issue of multiplicity, which has to do with when your roots, or your factors, the factors, basically are raised to a power. So if you have something to a power up here, whether or not that power is even or odd will dictate what happens around that intercept or around that 0. So in this case, if you have n as an even number, you're going to produce a bounce at that spot, which means you basically get a little mini parabola. Now, of course, more stuff can be happening in your graph. That isn't saying anything else, but basically you are going to bounce off locally. So in other words, it's going to hit and then come back. And of course, whether it bounces that direction or that direction will just depend on what the graph's doing in that area. On the flip side, if you have that power of a single factor or a single root being, is that a root? I want to say it's a factor. Power of that factor being odd, then basically it's going to produce what we call a slide. Basically, it flattens a little bit and then goes through. This one's a little harder to see. I think it's easy to kind of like sort of slide through or to just kind of gloss over it as you're looking through. The biggest thing to note is that it doesn't go like this. That's different because it produces extra zeros. It just creates basically a mini cubic at that spot. So right at that 0, it's kind of like it flattens for a second, and then that flat spot is where we get that 0. So odd roots give us what we call slides. And think of it as a slide because it's kind of like woo. The sound effect comes along for the ride. And the other one we call a bounce because the graph literally bounces off. And again, bounce, slide, noodle, bowl, these are not formal terms. They're just descriptive terms that I think capture the idea really nicely and get it visually and aesthetically in your head in a really valuable way. But they are, again, Franklin specific, not mathematical in nature. So there are all the biggest ideas here. Everything else, as I said, is just connecting the dot. So let's actually bring all these dots together and connect them by doing the 2 problems that are built into this essential skills quiz model. The first of those, I know the video description and like the caption or the section title will give you a name for it, but basically we're looking at negative x times x plus 1 times x minus 1 times x plus 2. And our instructions say to sketch the polynomial function and be sure to include all intercepts. Now, you're not prompted for specific information, so you don't have to write this out, but because of the fact that I'm trying to talk you through this and make this as visual as possible as well, I am going to write that information in here really fast. So what we're going to start with is we're going to try to figure out what the degree is of this polynomial. And that can be a little awkward the first time you check, just because it's not written as terms, so we can't just find the first term and go, okay, the biggest degree is this. Instead, we have to sort of imagine multiplying this out into standard form and see what that first term actually looks like. And that will help us with both the degree and, of course, finding the value of a, which is essential. Those 2 things combine into what we call the leading coefficient test, and that's going to give us what we're looking for here. So looking in here, the way we calculate that is we take the degreed term of each of these and we just multiply them out, as though we were going to multiply out this entire massive polynomial. That'll give us negative x squared, negative x cubed, negative x to the 4th. So whatever this thing is, it would begin with negative x to the 4th as its leading term. So the degree is therefore 4, which makes this even. And that means we're going to have a bowl as far as our shape between noodles and bowls using Franklin terminology. And then lastly, a is going to be negative 1, which is less than 0. That combination tells us we're going to have, in Franklin terms, a negative bowl. So for us, negative bowl is really helpful. What that means is it's going to start and finish like a sad parabola. That's like a frowning parabola there. I want to fix that. You can be frowning and not be sad. So a frowning parabola would be. So it's going to start low and end low. It's almost like We don't know exactly what happens in the middle. That's going to depend on some other stuff, but we know the end behavior. And so that's going to help us kind of start and end our graph. So with that in place, the things that remain are going to be finding our actual intercepts here. So to find those intercepts, we look at each of the individual factors here, and we figure out what would make each one equal to 0. So again, the problem doesn't explicitly ask us to state them, but I'll state them just for simplicity. We have 4 x-intercepts here. Those x-intercepts are going to be 0, 0, which by the way is super convenient. Since 0, 0 is the origin, it's on both the x and y axis. Therefore, that's going to be our y-intercept as well. So I'll just go ahead and make a quick note that that's y-intercept as well. We'll have -1, 0. We'll have 1, 0. I'm just literally reading those factors left to right and figuring out what makes each one equal to 0. And then we'll have -2, 0. So from here, I'm going to go ahead and label these. And I'm going to spread them out a little bit. We'll label them numerically so that we have them. I'm going to make that one -2, that one -1. We'll get this one as the origin, 0, 0, and then we'll have 1 right there. So there are our pieces. I'll label them in just a second. There's no 1 raised to a power, so there's no multiplicity issues to go through. All we need to do is now connect all those dots while adhering to the proper end behavior. So that means we're going to start down below. Then we are going to proceed through the first one. Then we're going to go back down through the second one. Then we're going to have to go up and through the origin, because that was our third one. And then we'll proceed downward, or back downward, towards the fourth one. And basically we get this nice shape. It looks a little bit like the letter M. I sound like Sesame Street. Today's video is brought to you by the letter M. Letters don't taste good. Whatever. I guess M&M's taste good. So in any event, there's our shape. Like, we've got basically everything, but we should label those intercepts themselves. So this was -2, this was -1, this was 0, and this was 1. And that is enough. If you're looking at this feeling like, well, shouldn't we label something else? Well, yeah, you could label this x, and you could label this y, or f of x. You could also draw a little arrow here to indicate that that's f of x. But unfortunately, there's no other way for us to find this, this, or this without using calculus. So basically, there's no reason to worry about that. We're just looking for representative stuff. We know that somewhere in between -2 and -1, there is a maximum. Same thing for between 0 and 1. We know there's 1 between -1 and 0. But we don't have the tools right now to find those without a graphing calculator, and this question is not about a graphing calculator. This is about your ability to sketch out a polynomial without having any reference tools. So that's exactly what we're looking for. So in a sense, that's a really strong start. We got to see a nice negative bowl. I will point out, by the way, though, if you were trying to translate this mathematics into your eating, don't put noodles in your bowl and then flip it upside down. The noodles will fall out. But I suppose that isn't even needed to be said. The second and final problem from this section, yeah, it's a pretty short one, is asking us to sketch a polynomial function as well, and just based on sort of the conservation of effective learning tools, if the first one was a negative bowl, you can anticipate this one being a positive noodle. And it's not going to disappoint us. But having said that, let me still walk you through each of the pieces. And I've just left the sort of organizational stuff from the previous problem here so that way it's a little more quick and accessible for you and for me. So in this case, we want to first determine the degree. And I'm going to follow the exact same approach that I did on the previous one. Degree is a little bit harder to find when we're given something, a polynomial in factored form. But in this case, we'll do the same thing. We have a leading, or in the first factor we have x, but it's squared. And then in the second one, we have an x, but it's cubed. So that's going to give us x squared times x cubed is x to the 5th. And then, of course, there'd be more terms. The important thing for us, though, is that that gives us a degree of 5, which is odd. Not odd in like, that's weird. I can't believe that's 5. But odd in the sense that, like, it's not even. So therefore, because it's odd, we're going to have a noodle. In fact, I'll go ahead and tackle that right down here. We'll have, again, a Franklin noodle. And then for a, looking at the leading coefficient, there were no other values to be spread out, no scalar, no negative sign, so our a value is +1, so we have a positive noodle. And again, that helps us because it tells us the end behavior. Our graph is going to be heading to -infinity on the left side, so our left end behavior is as x approaches -infinity, the function approaches -infinity as well, but on the right side we'll be approaching +infinity. So again, whatever our shape looks like, it's going to look like this on the ends. So super helpful. That basically gives us everything. All that's left is determining our intercepts and exactly how they appear on our graph. So looking up here, again, looking at each factor, we have x plus 1. So an x-intercept from there would be -1, 0. We're talking whatever makes it 0. And then, of course, our second one, x minus 2, will produce a 0 at 2, 0. Now, having said that, that's not exactly all the information we can mine from this factored polynomial, specifically because of the fact that we have those powers there. There's some multiplicity in fact, there's multiplicity for both of those two factors. The first one has a multiplicity of 2. So at -1, we have a double root, and a double root is going to produce a bounce. Typically, though, you'll see someone just kind of write a double. Sometimes I've even seen students write this, although there's some ambiguity with that notation. If you're going to do that, I might do a D for double. And the second one, x minus 2, is to the third power. That's going to produce a that means we have multiplicity 3, which is going to give us a triple root. And of course, as far as shapes, the double root produces what we think of as a bounce. It'll create like a mini parabola with its vertex sitting on there. Again, it's not a parabola, but it looks that way. So I'll use that familiar mathematical language. And then basically we have 2, 0, which has a triple root, and that's what we call a slide. It's got that little sort of cubic thing right at its locator point or its center. And so we're going to see a shape that looks like a flattened spot right there, either that way or that way. It just depends on the shape. So before we do that, let me just make sure we get our y-intercept correct. That is the one unique element of problem number 2. So looking in here to find our y-intercept, we're always going to plug in x equals 0. So if we do that, we're going to get, well, f of 0 is equal to 0 plus 1 squared times 0 minus 2 to the third. And if we multiply this out, we get 1 to the second times negative 2 to the third, which is negative 8. So our y-intercept is going to be down at negative 8. And the negative 8 part doesn't have to be like spaced out. We don't have to go ahead and go 1, 2, 3. That's not what we're looking for. We just need to know that it's below the x-axis. That'll ensure that everything is sketched out correctly. So I'll wait on sketching that. Instead, I'll put down my 2 intercepts. So we have negative 1 right there, where we're going to have a bounce. And then we're going to have positive 2 over here, where we're going to have a slide. Nice triple root. And then we again know that it starts low and ends high, and that it's going to bounce here, and it's going to slide here. So I'll go ahead and just kind of make those notes for a second so that we see them. For now, let's go ahead and sketch this out then. So basically we're starting low. We've got to bounce off this first one, and it came a little flat. Let me go. There, my computer did something weird there. So we're going to go ahead and go up and then bounce off this one. Then we're going to have our y-intercept here. So I'll go ahead and, in fact, sketch that in there in green. There's our y-intercept. In fact, I'll go ahead and even label it negative 8, just so we already have it. Then we'll continue upward, which is exactly what we're expecting. I'm going to flatten it through the slide, and then proceed upward. From here, the only thing that I'd be left with would be to label these pieces as negative 1 and 2. And then I would like to have my little arrow there to indicate that this does continue onward in those directions. But basically that's sufficient for us. In this case, the one thing that we don't have that's sort of an important area of the graph would be how low this minimum is and exactly what x value it occurs at. But again, that's something that would require us to use calculus. In this case, we could solve this with calculus. Or we would need a graphing calculator, but that's not the focus of the first half, question number 7, Essential Skills Quiz and Honors Pre-Cal. So you don't have to worry about that. Which means that things are complete. So that's going to do it as far as new problems on here. So just as kind of a quick recap, what we addressed in this video was sort of all things Noodle Bowl, which in Franklin terms is our way of describing sketching polynomials in factored form. So we talked about how parity affects that as far as the degree. So even degree produces that bowl where the end behaviors are the same on both sides versus an odd degree, which is going to produce that opposite end behavior. Combining that with the leading coefficient sign, whether it's positive or negative, will actually work out nicely. If it's positive, we're going to be opening upward in a noodle or in a bowl situation and starting low, ending high in the noodle situation, or reversed if our leading coefficient is negative in each case. And then lastly, we talked about how multiplicity does affect the shape at a particular intercept, in particular the x-intercepts, obviously. We get bounces when we have an even multiplicity, so 2, 4, 6, 8. Who do we appreciate? Or an odd multiplicity produces what we know as a slide, where we get that sort of mini cubic shape. After that, we sketched a negative bowl and a positive noodle, and I think we did everything pretty sufficient. Like, this is a fairly short video because I think that it's a really consistent skill. My accelerated class did great with this last year. Students seem to hold on to the noodle bowls, which is good because if you drop them, you got to pick up all the noodles. So yeah, we'll go ahead and call it right there. Thanks for watching. I hope this was informative. If this was a skill that you needed some support with, hopefully the key ideas in tandem with these two problems being worked out will be an assist to you. And again, don't feel like you have to write out stuff like I did here. You don't have to write out the degree and A in shape, but those are the things that are happening in my head as I work through these problems, which is obviously what I'm trying to model in videos like this. I'm trying to talk aloud, which, yeah, I wouldn't recommend in your ESQ itself, but on the ESQ model, it's probably a great idea to get yourself back into that mathematical mindset. So in any event, thanks one more time for watching, and yeah, have a great day. I was going to say like and subscribe, but this isn't those kind of videos. So yeah, just bye. Stop right there.